Okay, I have an example where we have to do something where we have to compute the determinant. That's example from page 17. That's the kind of metrics on that page. So what I will do, I will use this actually this process of computing the determinants. It's sometimes called row decomposition or first row decomposition because we use the first row for that. So I'm looking at the first row. So the first element of my row 1, actually I have all of them here, 1, and I have to multiply it with a smaller determinant, this one. And that smaller determinant, here it is, 2, 7, negative 3, 4. Now I move further along my row, element 4, I crossed out everything underneath, everything to the right and everything to the left. The remaining bits are negative 1, 2, and 7, 4. So the next term in my expansion or row decomposition will be negative 4 because this element comes with a negative. Remember, we alternate the signs. And we multiply by the smaller determinant. Here it is, negative 1, 7, 2, and 4. Negative 1, 7, 2, and 4. Now the last element here comes here. It's element 5. I crossed out everything underneath, everything to the left. That's the remaining smaller determinant. And so the last term in the expansion is plus 5. And then my smaller determinant. Now, for each of these three, we have to do the computation. So, like if I compute this, it will be the product across this diagonal. Take the product across this diagonal. Something we can compute actually from the top of our heads, can we? 2 times 4, it's 8, plus 21, it's 28. Do I have it here? Yeah, 28 and 29, sorry, 29 times 1. Here we have negative 1 times 4. Negative 1 times 4, it's negative 4, and take another 14, it's 18. So it's negative 18 times negative 4. And this one is negative 1 times negative 3, which is 3. And take 4, it's negative 1 times 5. If you compute everything together, 29, 4 times 18. How much 4 times 18? It's 8 times 72, isn't it? Yeah, it's 72. And take 5. 29 plus 72, it's 101. Take 5, it's 96. So the determinant is, in fact, 96. Any questions? It's a long process. Every step of this process is a very simple thing, but you have to follow the routine. You have to follow the routine, and on a few occasions we would need to see if you can follow that routine. I have actually, determinants have lots of interesting properties, and they have lots of connections with the things we did before, like a system of linear equations. You can see this title. We will come to this title in a second. What I can tell you, well, before we go down there, I will tell you this. This process, which I call the row decomposition, in fact, you can do this row decomposition with any row or even column. And I'll have this demonstration for you here. Look at this. I can take this. Let me just, instead of using the first row, I can in fact use the first column. So I can take this element, cross out everything underneath, cross out everything to the right, multiply by the smaller determinant, and then I move my cross not to the right, but down, and I take this element. I cross out everything above and below, cross out everything to the right, smaller one, it will be a smaller determinant, and then I do it again for the last element. This will be the column decomposition. Well, surprisingly, I mean, it's a subtle, deep result, but actually the result of this decomposition, if you follow this routine with the first column rather than the first row, the result of this will still be the same. I have the details here. In fact, here we go. So if you go your first element, and once in a lifetime we do it. So I cross it out. The companion or the minor, the associated minor, would be like a very nice language. It's a nice place to use this term. The associated minor is the same. Here it is. Now if I move it down, then the associated minor will be this minor, 4, 5, and -3, 4, everything which is left. Pay attention, you see I have +1 rather than -1 because we alternate the signs. And the last term in my expansion, column expansion or column decomposition for the determinant, will be +2, and the associated minor is 4, 5, 2, 7, this minor. 4, 5, and 2, 7. If you compute each of these determinants, each of the smaller determinants, and you add them up together, the result will still be 96. Here it is. 1 times, this one is 29 again, it's the same as before. Here we have 1 times 12, take 15, it's -3. Oh, no. Plus. We multiply across this diagonal and take away the product across this diagonal, but we have extra negative, so it's plus. So it's 16, I said 12. 16 plus 15, 31. Yeah, that's the one. And here we have, be careful, 28 take 10, it's 18. Yeah, this time I didn't make a mistake. If you add these things together, 29 plus 31, it's 60. And another 36, it's 96 again. Yeah, actually, that's exactly what I was about to say. In fact, you can do these decompositions, although we use the first row for the definition, and most of the time the first row will do, but you can do these decompositions with every row or every column. So for instance, I have another example. I won't be doing the computations of that. If you use this, say, for instance, second column, you take the element 4. I'll show you the details, but I won't be computing that. -4 times the associated minor, 1, 2, 7, 4. Then you move your cross down. So you have number 2, and the associated minor, look at this. I crossed out everything left and right, everything above and below. The associated minor is this 1, this 5, this 2, and this 4. Here it is. Now I move this cross another step down, -3. Associated minor will be this -1, this 1 and -1, and this 5 and 7. So the last term in this expansion will be this term. If you finish these computations, I have it here, but I don't want to do it. If you finish this computation, I'll leave it for you to finish. You will still find 96 as a result. Yes?
What if you do it along the diagonal?
No. Not anymore. No. The freedom of choice ends here. Columns or rows. Yes.
The signs of what you're trying to
Yep.
do. Shouldn't for the first one, because you're doing the second row.
When I did this one, you mean?
Yeah.
You well, I was hoping somebody will ask this question, and I was like almost lost my hope by the end of it. Yeah, you're right. Actually, when you do first row or the first column, I said to you we alternate the sign and we start with plus. But when you go for the other rows or other columns, and I put here -4, so I started with minus, so I started with the minus and I start alternating my signs. Now, yes, when you go for the third row, it will be like the other way. Now, the general rule, I mean, like it sounds a bit slippery right now. The general rule goes like this: do I have it here somewhere? So when you do this expansion, not necessarily with the first row or with any other row, you put your minus with this combination. In fact, when you alternate with where you sum up the indices, j plus k, and that will be the clear indication of the sign you choose. So for instance, this 4, remember when I look at this 4, the index here, the row index is 1, the column index is 2. Sum of the plus of it will be 3, odd number. That's why this 4 in the expansion came with the minus. So in general, when you go any some other row, not specifically the first one, and not specifically the first column, that's the principle you follow when you choose your alternating signs. Yes?
Reduce matrix first and then do it, so you can get more zeros.
Yes, that's something we will just discuss next time. The determinants, they have connection with the Gaussian elimination process. It is like an almost straightforward connection. And you sometimes can use the Gaussian elimination to your advantage when you compute the determinants. Yes?
There's a -3 there. 3 did -1 to the power of 3. Okay, that'd be 5.
You refer to this -3?
And so that'd be -1.
And that's a good observation. Thank you very much. Thank you very much. That's a plus.